All right, so thank you for the introduction. So I'm Eric Vinn. I'm a PhD student at UC Santa Cruz, here to present our work on LeanLTL, which is a unifying framework for linear temporal logics in Lean. So I want to start this talk by going into a bit of the motivations for why we worked on this project, because my background is not in ITPs. It is in verification of cyber-physical systems. So we mostly try to verify learning-enabled cyber-physical systems, like self-driving cars, drones, things that interact with the real world and have machine learning-based components. And often these systems are safety critical. Like a self-driving car, if it crashes, lives could be lost. It's really important that they work correctly. And in general, it's easy to test these systems, but it's really hard to verify them and to make sure they work correctly all the time. One approach that our group has been looking at is compositional verification of these systems. And when you're trying to verify these properties, a nice way to express them and reason about them is through temporal logic, or linear temporal logic in this case, which makes it really easy to reason about system properties over time. So LeanLTL is a framework for just that, for reasoning about linear temporal properties of systems in Lean 4 with convenient syntax and automation. We're applying it in upcoming work as part of a larger verification framework for verifying cyber-physical systems, where we've already used it in a simplified but non-trivial automatic emergency braking case study, which has some proofs that I would consider non-trivial, but I'm not a Lean expert. So they're available in the LeanLTL repo if you want to take a look. And here's a little snippet of what the library looks like, where you can see we have this LTL formula declared up top, which just says that for all infinite traces, that's the left turnstile with the I, if we have this variable n that starts with 5, and it is always true that the next value of n is equal to the current value squared, then it is always true that 5 is going to be less than or equal to n. So here we have a short, simple proof in Lean. And this is an undecidable theory. So you can't solve this in general. There's no decision procedure for it. But in Lean, you can do it very simply by just using this reduction and then using a Lean tactic that can handle it. So with the motivation covered, I want to jump into background, specifically starting with linear temporal logic and how it's defined. So it's defined over a finite set of propositional variables. These include the standard logical operators like not, or, and, implication. And in this logic, time is discrete and over an infinite horizon. In its most basic form, you just have two temporal operators. The next operator, which says that something must hold in the next time step, and the until operator, which just says that something must hold until this other thing holds. And if the second property never holds, then the first must hold forever. And you can define additional operators using these, like globally, which is this G that says that something must hold in this and all future time steps, and finally, which states that something must eventually hold in the future. And just to visualize what these might be, if we had an example that was covering traffic lights, you might have a property saying, if the light is currently yellow, then in the next time step, the light must be red. Or if you wanted to say that globally, finally, the light is green, that just means that the light will always turn green at some point in the future. So these are useful properties you might want to prove. This is fairly simple logic, but you can soup it up with some extensions. So one common one is the finite version of linear temporal logic, which just, instead of looking at an infinite time horizon, changes it to look at a finite one. And the only complication here is that the next operator can be a bit undefined on the last time step, so you need to split it into two that decide which value to return, true or false, on the last time step. But a lot of the real power comes in with this linear temporal logic modulo theories, which add support for SMT-style theories into the logic. And critically here, the next operator can be used on values inside these theories. So in this example, we can say, assuming a equals 0, and it's always true, the next value of a equals a plus 1, then eventually, in the infinite trace, a will be greater than 10. And so this adds a lot of complexity, which is why we need interactive theorem provers. Because while LTL and LTLF are decidable, and there's efficient decision procedures that exist for them, if you add theories, you can increase the complexity. And while for some theories, you have decidability, especially for some decidable theories, you have full decidability. If you use undecidable theories, it's clearly not going to be a decidable problem when you add them to LTL modular theories. And again, from our example at the very start, nonlinear arithmetic is one of these. So for this reason, we've built this library around an interactive theorem prover, sort of an escape hatch, so that the user can always provide a proof, even if automation fails. So as project overview, LeanLTL is a framework and Lean4 library that can be used to reason about linear temporal properties of systems. It has core types for modeling temporal properties across infinite and finite traces. It has support for arbitrary Lean expressions inside formulas, which sort of fill the role of theories. It includes convenient macro syntax for creating these LeanLTL formulas. And it also supports some preliminary automation to simplify reasoning. And this is an in-progress work, so we're hoping to add more, which I'll get into towards the end of the talk. So I want to discuss a little bit at a high level of the core library. And the most basic type in here is traces, which just model the properties over time. They can be finite or infinite. And the next operator that I discussed earlier is enabled by this a shift operator in LTL. And so just as an example, from the traffic light, you might have a trace that says whether or not a light is green, going true, false. And you might have one that represents the current queue at a traffic light, natural numbers. Then building on this, we have trace sets and functions, where trace sets represent a formula in LTL by its set of satisfying traces. And this lines up with MathLib's definition of set. And then trace functions are how we implement these operators in LeanLTL with the that map from a trace of a certain type to an option type. And that's how we represent this exceptional behavior that you might get if you go off the end of a trace. And to extract these values from this option type, we have a weak and strong get operator, which are basically equivalent to the weak and strong next in finite LTL. And so here I've included two examples of the OR operator and the add operator as trace sets and trace functions using this map utility. So to aid in writing LeanLTL formulas, you don't want to write it in that format. So we have a macro that you can write it in a nice, simple, readable way that resembles normal LTL, and it will compile it down. And we use these arrow bind operators to implement these get operations, which are how you extract the values if you look into future time steps. And we also have some preliminary automation centered on simp sets, which can be used by simp to transform the LeanLTL formulas. The primary example here is push LTL, which just basically pushes the satisfies operation as deep as possible, transforming the LTL operations into what essentially are the first order logic semantics. And then oftentimes you can solve these directly once you've done this if it's a simpler proof, but just using built-in Lean tactics. So I now want to highlight some examples and some applications of this. So to start, here's a worked example in our paper. It's a lot of text, so I don't want you to focus on reading all of it, but it's just to show the syntax. And starting with a lot of properties at the top, we might want to prove about how this sort of traffic light system works. We might want to prove a goal property at the bottom, like it is always true that if one traffic light is green, the other is not green, and vice versa. Because that's a safety property that means that we will not have two lights green at the same time with cars crashing into each other. And a proof of this is really simple. We just use the utilities, a few utilities in the library, and the simp sets, and then we can reduce it into something that Lean can handle using the T-auto tactic. We also show that LTL and LTLF can be directly embedded into LeanLTL, preserving their semantics. And again, as I said earlier, we've applied LeanLTL as part of an example verifying compositional simplified automatic emergency braking system. And these are some non-trivial proofs using undecidable theories. So they couldn't have been accomplished just by using a solver. And we're also, again, actively working on incorporating LeanLTL into other verification tools to hopefully be applied to aid in verifying real-world systems. So again, LeanLTL, a unified framework for reasoning about linear temporal properties in Lean4. This is preliminary work, so we're now looking to add automation for the decidable fragments with decidable theories, best as a Lean tactics. And we're also wanting to show the full embeddability of LTL modular theories and LTL F modular theories, and potentially add other operators like past time and bounded time operators. Thank you.